Hello all. In this lecture of today, I'm going to do a little bit more about little bit more about matrices. And as I told you that there would be some few around 2 to 3 lectures which are going to be dedicated to your you can say BSc level stuff or probably 12th class stuff. So in that series, today will be the last lecture. From tomorrow onwards, we are going to go through some advanced um, things in matrix algebra, and lately we'll start with linear algebra. Uh, you must note that both linear algebra, the not good know-how of matrices, and linear algebra would be very helpful for understanding the framework of quantum mechanics. In general, the physical concepts of quantum mechanics are quite counterintuitive, and when it comes to exam, I would suggest that even if you don't understand or probably if you don't have time to go through each and every concept, you must know how to mathematically apply those concepts and get answers. Okay, so getting an answer would actually require you to be very sound with uh, linear algebra and matrices. Okay, so that is why I have taken this particular topic. Um, I hope you'll keep some patience, and then as time progresses, you'll be able to understand the importance of these lectures that we are doing right now. Okay, so done enough of the definitions. So these definitions have been done till now. I guess these are just definitions, and a few questions also we've done. Yesterday I gave you a question at last. I will do it after doing a theorem. Okay, so for that you just keep a little bit of more patience, because I want to introduce a theorem. This particular question I'll do after a theorem, and that theorem I will teach you in your linear algebra. So I want that particular theorem to be applied, and then you can do this question. Okay, so that we'll do in linear algebra. Today let us begin with another concept of finding the rank using transformation, elementary transformation. So it becomes very important that you should know what are elementary transformations. And before that, a small topic that I left actually, I'll just do it actually. It's not going to be asked in exam, but okay, you should be knowing all these things. So I'm doing it for you. The topic is called as the adjoint of a square matrix. Adjoint of a square matrix. Okay, so what is an adjoint of a square matrix that we have to do? So let us consider that we have this A as a matrix given by A11, or I can write for simplicity, I'll write simply A1. Okay, let us write A11, A12, A13, or I'll do this thing. So I think that would be easy for us to. I'll do one thing. I'll use some different notation, so that otherwise all these things will become so much muddled that you will not be able to understand. So I'll use easier notations. Okay, so I'll use one thing, that is for the row one. I'm going to use A1, A2, A3. For row 2, this is B1, B2, B3, and this will be C1, C2, C3. So let A be a square matrix. This is a square matrix, uh, and we know that we have to find the adjoint. We have to find the adjoint. Uh, so before adjoint, let us first find a matrix which is formed by the cofactors. So yesterday I taught you about cofactors, if you remember. Minor times, if I have to find a minor through aij, then it was simply, let's say if it is a11, if I have to find the minor along a11, so let us say this is your matrix, this is a11, this is a12, this is, let's say, a13, this is a21, it is a22, it is a23, and it is a31, let's say it is a32, and let us say it is a33. So minor through a11 would be this determinant, this matrix of this determinant of this submatrix. Okay, so this will give you the minor, and if you multiply it with minus 1 raised to power 1 plus 1, so you will get the cofactor. So C11 would be this. So let us first form let us first form a matrix using cofactors. using cofactors. Okay, using cofactors. So this will be a matrix. Let's say this will be a matrix, and here I'm writing the cofactors C11, C12, C13. This will be C21. This will be C22. This will be C23. It will be C31, C32, and C33. So this is your cofactor matrix. And understand this cofactor matrix. I'm just removing this. I think it's not required as such. Okay. Okay, and all of you know that the cofactor C11 would be what? So I'm writing it here so that even if you are if, once you are revising the concepts, then you'll be able to understand what would be C11. So C11 would be just give me a minute. Okay, C11 would be what? C11 would be simply B2 C3 minus B3 C2. So you have to find you have to find minor through A1. So for that, delete the row and the column in which A1 belongs and take this determinant of the submatrix. So this will be like B2 C3 minus B3 C2. What would be C12? This one. So for this you have to multiply with minus 1. Remember, because see 1 plus 2 is 3. So minus 1 into what would be it? So it would be A1 and so sorry, it would be equals to uh, so what you have to do, you have to I have to find the this thing. So it will be what? It will be B1 C3. I should write it here now so that you'll be able to understand. So in order to find C12, I'm writing it here. It would be negative of C. It would be negative of B1, and then I will write B3. I will write C1 and C3. So concept is very simple. My if I have to find the minor through A2, I have to remove the row and column in which it belongs. I have to remove the row and column in which it belongs. So you have B3, B. So this and this gets removed. So you have B1, C3, C1, B3. So this will be like B1, C3 minus B3, C1. Okay. Similarly, I'm writing what would be C13. Just think about it. C13 would be B1, C2 minus B2, C1. So it will give you C13. Similarly, what would be C23? C23 would be A2 C1 minus of A1 C2. What would be C31? C31 would be simply A2 B3 minus B2 A3. And what would be C32? So I think it is quite easy for you to see, and I think you can confirm it on your own. I'm just writing it for your convenience. Okay. So what I have done, I have first taken a matrix. And then there are few other remaining. So I'm writing those also. So what would be C21? C21 would be simply A3 C2 minus A2 C3. Okay. And what would be C33? I think C33 would be remove this thing and this thing. So it will be A1 B2 minus A2 B1. And what would be C22? So C22 would be this would be, I think this would be A1 C3 minus A3 C1. Okay, so I hope this is something that you know. Okay, so what I have done from a matrix A, I have found this matrix of cofactors. I have made the matrix of cofactors. Okay, this matrix of cofactor, when the transpose is taken, so I'll write it here. So I'll write it here so that you should better note it down. So the transpose of this cofactor matrix, transpose of this cofactor matrix, this cofactor matrix is what you is called as your is called as the adjoint of the matrix A, is called as the adjoint of matrix A. Okay, so why it is required? So whenever you have to find an inverse of a matrix, whenever you have to find an inverse of the matrix, then you need this adjoint. Okay, once you know this adjoint, only then you can find your inverse. Otherwise, then there are different methodologies. Like for example, I can do one more thing, and from that also I can find inverse. But overall, this would be the basic elementary strategy. So I hope till now everything is clear. Am I audible now? So I think just give me a minute. So if it's possible, I'll see who all are watching it. Okay, so there are people watching it. Okay, okay, Sindhu is right. Okay, so now this is called as the adjoint. I think this is quite clear. I'm going to take one simple example and then we'll move further. Okay, I'll just take a simple example to illustrate this and then we'll go further. So let us try to write the adjoint of this matrix A given by 1, 2, 3, 0, 5, 0, and then this 2, 4, and 3. I think this is 1. Okay, so what I can do is, if I have to find the adjoint of this matrix, then what I have to do? See, if I have to find the adjoint of this matrix, first form the cofactor matrix. First form the first thing I'm writing it. First form the cofactor matrix. First form the matrix of cofactors, or otherwise I should write. First form the matrix of cofactors. Okay, so in order to make the matrix of cofactors, now let us do it quickly. So I'm writing what would be C11. C1 would be 15. What would be C12? C12 would be, I think C12 would be 0. C12 would be simply 0. What would be C13? So it is actually minus of 0, minus of 0 is 0. C13 would be what? It would be minus of 10. What do you think C21 would be? So C21 would be minus 6. Because see, if I have to just think about it, so if I have to, okay, 6 minus 12 minus minus, okay, what would be C22? Okay, so in order to find this thing C22, it would be, I think 3 minus 6, 3 minus 6 is minus 3, so it would be 3 minus of 6, so minus 3. Okay, what would be C23? Just think about it. What would be C23? It would be 4 minus 4, I think 0. Okay, what would be, okay, who's this? Somebody, sorry. Okay. So let me help the student. Oh, not directly. Just give me a minute. No. Okay. So okay. So this is how you do it. And if I want to find C31, I think this, just I'm not giving you much questions. Okay. See, a student is asking that this topic, does it come in the exam? The answer to this question is no. Okay. Now why am I doing this? So that you should, once you are doing matrix theory, you should know each and everything. I'm not going to solve much questions on the adjoint. I'm going to solve much questions in the eigenvalues and eigenvectors. But I want to formalize it so that whenever you are going to study linear algebra, which forms the basic structure of your quantum mechanics, then you are not at a deficit with regards to anything. So that will help you out anyway. So that is what is my suggestion to you. That just keep patience. I told you just keep patience for 3 days. Once you keep these patience, then you'll see how fruitful it is. So what would be C31? C31, okay, it will be, I think, minus of 15. And I think C32 I can write quickly. So minus of 15. C32 would be equals to what? C32 would be equals to, so C32 I think it would be equal to 0, I guess. And C33 I think equals to 5 minus 0. So it will be 5. Okay. So this is how you can construct a cofactor matrix. This is how you can construct a cofactor matrix. This is how you can construct the cofactor matrix. And what is a cofactor matrix? This is how you construct your cofactor matrix. C11 is 15, you already know. C12 is already 0. C13 is minus of 10. Then you have 6, then you have minus 3, then you have 0, then you have minus 15, then you have this 0, and then you have 5. And then you can take a transpose of it. And then you can find your adjoint. Okay? Then you can find your adjoint. So adjoint A would be the transpose of this particular thing, and it would be, I think, 15 0 minus 10, 15 0 minus 10. Then you have 6 minus 3 and 0, and then minus 15 0 and 5. I hope it is clear. So this is how you do adjoint. I think this is more than sufficient for you with regards to adjoint. Now let us move to few properties of adjoint, and then we'll continue further. Let us do a few properties of adjoint, and then we'll continue further. So some properties of adjoint. So I'll let you know when we are going to lay much focus on. Then those topics are more often asked in the exam. Okay, those topics are more often asked in the exam. Okay, so always remember that the first thing that you should remember is, so whether I it's just I'm writing it here. Okay, the first thing that you should remember is that the product of a matrix and its adjoint is commutative. Product of matrix and its adjoint is commutative. Okay, this is the first thing. That is, if I multiply adjoint with A, that is matrix A, or I pre-multiply A with the adjoint of A, they are one and the same thing. And what do I get? I get determinant of A into identity matrix of order n. And from here only we derive one thing, that if I want to find the inverse of a matrix, if I want to find the inverse of a matrix, how am I going to find it? So from here itself you can do that. Here itself you can do that. Okay. Further, you can also note one more thing, that if I'm just writing, if A is n road means you have n rows, n road squares singular matrix. Singular matrix. If it is a singular matrix, then determinant would be 0. So then adjoint A into A and pre-multiplying A with adjoint A would give you what? It would give you a null matrix. It would give you a null matrix. So I'm writing it here null matrix, otherwise you will not be able to understand. It will give you a null matrix. Then further, think about this. Now if A is a n road non-singular matrix, then obviously if it is a non-singular matrix, then the determinant of A would be non-zero. If it is a non-singular matrix, then adjoint A determinant is written as determinant raised to power n minus of 1. So all these three properties you can keep in mind. It's not that much required, but you can keep that in mind. Okay. Okay. So now let us move further. Uh, Let us try to do one question. Achha, two or more properties let me write for you, then it will be more than sufficient. Another thing that you can write is that if I want to find, if I have this A and B as two square matrices, and then adjoint, I'll write adjoint AB is simply equal to adjoint A into adjoint of B. Sorry, adjoint B, I think, into adjoint of A. Just reverse. Remember this. Generally, people get confused. Adjoint AB is equal to adjoint of B into adjoint of A. Okay. If I want to take the transpose, so adjoint A transpose is equals to adjoint of A transpose. Okay. All these things I'm not deriving. I'm just writing it so that at least whenever you are free, or at least if somebody in from the jam also sees this course, then he's able to take the best out of it. Adjoint and adjoint of A. So if I'm doing adjoint operation two times, that is adjoint of A, then it comes out to be equivalent to determinant raised to power of n minus 2 times A. This A is a non-singular matrix. Remember, this should be a non-singular matrix. And one result I've already written, that if I have to find adjoint A determinant, then it is determinant of A raised to power n minus 1. Similarly, if I want to find adjoint A determinant, then it is equals to determinant of determinant raised to power n minus 1 whole square. So determinant A raised to power n minus 1 whole square. So all these properties, just keep them in mind. They're not going to be asked in your examination, fine, but still keep these things in mind. Update your notes accordingly. And now let us do a simple problem on this. Let us do a simple problem on this so that you are able to understand what I wanted to teach. So for example, if someone asks you in the exam that, let's say A is given to you. Let's say A is given to you. This is 3 minus of 3, 4, 2, minus of 3, 4, and then you have 0, you have minus 1, and then you have 1. And if I'm asking you to find adjoint A, then how you are going to achieve it? How we are going to achieve it? So as I've written already, that adjoint of A, sorry, adjoint of A is equals to A raised to A, determinant A raised to power n minus of 2 times A. Okay, so here instead of n, I can use 3 because the order of matrix is 3. So this is a 3 cross 3 matrix, so I can write that n is equal to 3. So if n is equal to 3, all I have to, and then secondly, also judge the nature. Just the nature. So if it is a non-singular matrix, so here also I should mention it. These two results are valid only if A is a non-singular matrix. Only if A is a non-singular matrix. If A is a singular matrix, then I have already told you that adjoint of A into A would give you 0 there. Okay. However, here adjoint of A has been asked. First thing that you should remember is try to find the determinant. So what would be determinant of this? Let us first try to find the determinant. So determinant would be 3 into 1 minus 3. This will be 3 into 2 and then 4 into minus 2. So I think determinant would be 3 plus 6, 9, 9 minus 8 is 1. So clearly it is non-zero. It implies that A is a non-singular matrix. A is a non-singular matrix. A is a non-singular matrix. Now we have just that A is a non-singular matrix. Now let us do this particular problem. That is, we want to find adjoint A. Okay, this is equals to determinant A raised to power 3 minus 2 into A. So in fact, what you can write, the determinant of A is 1. So determinant A is 1. So A raised to power 1 is 1. So adjoint of A would be nothing but the matrix itself. I hope it is clear. Please let me know. Please let me know if it's getting boring. So I'm going to start today. Please don't worry. I hope it is clear till now. Okay. Okay. So now, if you remember from your standard 12th also, inverse, I'm just writing it here. I'm not going to do questions from inverse. That would be a long thing to do. What is inverse of a matrix? So if I want to write inverse of a matrix, what is inverse of a matrix? Let us write that first. So if A and B are two square matrices, if square matrices, and such that you can say that A into B gives you identity. A into B gives you identity matrix. Then it implies that B is nothing but A inverse. Okay, and this is called as your inverse of A. Okay, this is called as your inverse of A. And similarly, we can say that A is equal to B inverse. We can say that A is inverse of B. Always remember, uh, always remember that every invertible. Now, for invertibility, what do you need? You need that your matrix should not be singular. So every invertible matrix possesses a possesses a unique inverse. Possesses a unique inverse. Secondly, uh, it should be the one thing is clear that square matrix for a square matrix A to have inverse, square matrix A will have an inverse. I should write have an inverse only if it is non-singular. That is, determinant of A is non-zero. Determinant of A is non-zero. That is only if A is non-singular. And once you know this thing, once you know that inverse exists, then what I have to do? All I need to do is I have to take an adjoint, which I have told you it is nothing but it is the I think transpose of the cofactor matrix divided by determinant of A. So this is how you are going to get the inverse of A. So this is how you define the inverse matrix. I'm not going to do question here. This is something that you know from your childhood. Okay. So all these things said and done. Let us not waste our time. And okay. So let us first focus on eigenvalues and eigenvectors, and then we'll again come back to the rank and solving some using some elementary row transformation that we'll do later on. But let us first address the elephant in the room. So basically, this is what is asked in the examination. So now let us do something called as eigenvalues and eigenvectors. And remaining discussion on you can say row transformations and column transformations, rank and system of equations we'll do later on. I hope some bit of system of equation you know. Still, I'll do that discussion later on. But let us first do the discussion of eigenvalues and eigenvectors. So let us first discuss the eigenvalues and eigenvectors. So at least that gives you some sort of excitement to this particular topic. Okay. So always remember that in your physics there would be lot many areas where you will find an eigenvalue equation. One of the most favorite equation, that is a Schrodinger equation, is also an eigenvalue equation, right? So in general, one cannot get over it. One has to understand what are eigenvalues, what are eigenvectors, and so on and so forth. Okay, so this is something that you should know. Okay, so any eigenvalue problem would consist of, so I'm just writing it here. So what is an eigenvalue problem? A into column x is equals to lambda times x. This particular problem is called as your eigenvalue equation. This is called as your eigenvalue equation. This is called as eigenvalue equation, and this lambda is called as the eigenvalue corresponding to A. This is called as eigenvalue corresponding to A, and this x is called as the eigenvector. So I'm writing x is called as the eigenvector corresponding to the eigenvalue lambda. So corresponding to eigenvalue lambda, you have this x as your eigenvector. So this is your eigenvector. Okay, so one of the most fundamental eigenvalue equations that you find in quantum mechanics is h psi is equals to en psi or simply e psi. Okay, so you know that in quantum mechanics this is something referred to as Schrodinger equation. Okay, and this is also an eigenvalue problem. This is also an eigenvalue problem. This is also an eigenvalue problem. Okay, so what do we do? How to solve this particular problem? This is quite easy to see that what I would do, I'll take the RHS to the LHS. That is, I'll do this a minus of. So I'll write it first ax minus lambda. Instead, I'll write identity x is equal to 0. I'll write a minus of lambda I x is equal to 0. Here what is identity? Here I is the identity matrix. What is I? Sorry, it is identity matrix of the same order as that of A. So identity matrix has the same order as that of A. Has the same order as that of A. Okay, so if A is of 2 cross 2, then identity will be of 2 cross 2. If A is of 3, then it order 3, then it will be identity will be a 3 cross 3 identity matrix. Okay. Okay. Now, in order to solve this particular equation, what we do, we take the determinant equals to. So what we know that from the I'm just writing here for a non-trivial solution. For a non-trivial solution, for a non-trivial solution, this determinant of a minus lambda I, which is also referred to as secular determinant. This is also referred to as the secular determinant. Secular determinant. This should come out to be equals to 0. And when you take this determinant equal to 0, what will happen? See, this is an n cross n matrix. This is an n cross n this is an n cross n matrix. And if you take a determinant, you'll get a polynomial of order n. So you have to solve solve a characteristic equation. Solve a characteristic equation in order to obtain the eigenvalues. In order to obtain the eigenvalues. I hope it is clear. I think this is something that you know, but still I have made you a revision. Please let me know if there was an error, if there is a lack of understanding anywhere. And why this has to be equal to 0? This is from the system of equations that for a trivial solution, this matrix, determinant of this matrix should be equal to 0. Because if it is non-zero, then I'll take an inverse here, then x will form a trivial solution. Are you getting my point? So if this is non-zero, if this is non-zero, then what I can do, I can take an inverse here. So x will be a what you can say trivial solution, that is 0, 0, 0. Like, so that is why for a non-trivial solution, the determinant of a minus lambda I must be equal to 0. This is referred to as the secular determinant. The equation that we get out from this is called as a characteristic equation. Once we solve this characteristic equation, we get the eigenvalues. Is that clear? Now what happens is, now from fundamental theorem of algebra, we know that from fundamental theorem of algebra, we know that if there is a you can say if there is an equation of degree n, then it can have at most n real roots. It can have at most n real roots. So what I'm saying is, if at all there is a equation of degree n, at most it can have n real roots. So what does it imply? So for example, from fundamental theorem of algebra, it implies that an n cross n matrix can have r eigenvalues in general. And what can be the maximum value of this r? Maximum value can be n, and minimum can be 0. That is, let's say if all the roots are non-real and all the roots are real, then it is equals to n. So you understand now, from fundamental theorem. See, a fundamental theorem of algebra says that an nth order polynomial, I'm just writing an nth order polynomial, has at most understand, has at most n real roots, has at most n real roots. So this is what your fundamental theorem of algebra says. At most. At most means at max. So n cross n matrix can have n eigenvalues. Okay, and it is not necessary. They may be distinct or they may be not distinct. So they may or may not be distinct. They may or may not be. They may or may not be distinct. Distinct means different. It may be possible that eigenvalues are same as well. They may or may not be distinct. The one more, let us just write a few more definitions so that you are able to understand. This entire eigenvalue set of eigenvalues that we get is called as eigenvalue spectrum. So what is your eigenvalue spectrum? If you can take it, I can write it in easy fashion. These are the set of all eigenvalues of a matrix. Set of all eigenvalues of a matrix. Set of all eigenvalues of a matrix is called as a eigenvalue spectrum. And let's say if there are, what I can say, if there are, I'm just writing, if there are, uh, we should not write this way, if there are roots. So for example, if I solve a characteristic equation, let us say, if I solve a characteristic equation and the equation comes like lambda minus 2 power 3 lambda minus 1 ki power 1. So I have three coincident roots. I have three coincident roots as 2. So 2 is appearing 3 times here. So if it has r coincident roots, then we say that what do we say? That multiplicity of this eigenvalue is r. Multiplicity of this eigenvalue is r. We say that the multiplicity of this eigenvalue is simply r. I hope it is clear. Okay, so I'm giving you a few questions. You try to do them and just let me know what are the answers in the comment section. I'll take a little bit of break. I'll come in 5 minutes. Okay, so I'm giving you a few questions. Till then, you just try to do this. So, question number 1, try to find the eigenvalue of this 2, 1, 0, 0, 2, 0, 0, 0, 1. You try to find eigenvalue of another matrix M given by 0, 1, 1, 0. Try to find the eigenvalue M, so 1, this I can write B, and this I can write C. So try to write eigenvalues of M, which is 1, 2, 3, and 2. Just try to write the eigenvalues of the matrix. Okay, so how to find the eigenvalues for the same? to find the eigenvalues, I've told you what you have to do. You have to do only one thing, that is first try to find the secular determinant for the same. So just try to find the secular determinant. So I'll do it for you. Answer number one. How to go about it? Just take m minus lambda I determinant equals to 0. This is what I have taught you. If you do that, you will get this as, I think, 2 minus lambda here. Here you get 1, here you will get 0, 0, 2 minus lambda, you will get 0, 0, 0, 1 minus lambda. Take a determinant, take it equals to 0. Take a determinant, take it equal to 0. Okay, so take it equal to 0. So I told you now, if there would be a, if I am solving a determinant, I will get a characteristic equation, and since it is a 3 cross 3 matrix, so the characteristic equation would be cubic. So you will get a cubic characteristic equation. You'll get a cubic characteristic equation, and then you can solve that particular equation. So what you'll get, you'll simply get 2 minus lambda square into 1 minus lambda. Then I think this is 0, this is 0. This is equal to 0. That implies lambda equal to 2 and lambda equals to 1. In fact, the eigenvalue 2 is of multiplicity 2. So eigenvalue 2 is of multiplicity 2. Okay, I know such questions are not going to be asked in the examination. Just focus on whatever I'm saying right now. Okay. Second question, how to do it. Second question, how to go about it. So it's again a simple question. I think this is quite easy to see that this will be minus lambda. This is 1 and this is 1. Try to take the determinant of it. The determinant will be will give you equals to 0, would give you lambda is equal to plus minus 1. So there are the eigenvalues are distinct. Eigenvalues are distinct. And similarly, you can also find this will be 1 minus lambda, this will be 2 minus lambda. Here you will get 2, here you will get 3. This is the third matrix whose eigenvalues you can find. I think 1 minus lambda into 2 minus lambda minus of 6. So this will give equals to 0. This will give you 2 minus of 3 lambda plus lambda square minus of 6. I think quite easy. Lambda square minus 3 lambda minus 4 equal to 0. And that I think it's easy to solve. You can write it as minus 4 lambda plus 1 and lambda equal to lambda is equal to minus 1 and lambda is equal to 4. I think it is quite clear. Please let me know yes or no. I think this is clear, but still just let me know this is something that you're following, right? Okay, so this will give you lambda is equal to 4 and lambda is equal to minus 1. I think this is quite easy to see. Is that fine? I think two people are attending. Anshul is attending and Monica. Is that fine, both of you? Kindly let me know. Okay. Now see, this is one thing that you should be remembering. See, this is something that you're going to do quite often. This is something that you're going to do quite often in your, what you can say, in your quantum mechanics also. So all these things are very important. Please remember. Okay, good. So let us move further. Now, once you know this eigenvalues, then you can also determine eigenvectors. Once you know these, once you know your eigenvalue, then you can also identify your eigenvectors. Okay, so let us take a simple example and understand so that things. Let us take one simple example. Let us take one simple example. I think from here, I think the simplest one would be to take the second example. Let us take the second example. Okay, let us take the second example. I think that is easy to show you. So if I take the second example says 0, 1, 1 and 0. This is 0, 1 and 1 and 0. Okay, this is your matrix. Corresponding to it, there were two eigenvalues. Corresponding to it, there were two eigenvalues. One was plus 1 and other was minus 1. Now, in order to solve this, what we take a column vector. We take a column vector x. Let us write it as x1 and x2. Okay, and I write this m minus of lambda I times x equal to 0. And what I'll get here, I'll get I'm doing it corresponding to this, and I'll do corresponding to this also. Okay, so what it will give me? It will give me minus 1, minus 1. Oh, sorry, this is minus lambda. This is also minus lambda. Okay, minus 1. Okay, okay. So because I'm taking lambda equal to minus 1, lambda equal to 1 only, no? So I think that is fine. So I'll take it as okay. So I'll write minus 1, minus 1, and then I will write simply 1 and 1. And this is x1, this is x2, and it is equal to 0. What I will get from here? I will simply get I will simply get minus of x1 plus x2 equals to 0. So that implies your x1 should be equals to x2. Okay, so x1 equal to x2 you can simply take as 1, and at times we normalize it also. Normalize it also means we divide it by uh, root over x1 square plus x2 square. So a normalized eigenvector would be 1 over root 2, 1 1, and if you don't want to write it in normalized way, then simply write 1 1. It is quite easy to understand. Is that clear? And if you use lambda is equal to minus 1, you will get 1 1 1 and 1, and then you have this x1 x2, and here I can write it will be equals to x1 is equal to minus of x2. So here I obviously I can say that the column vector would be 1 minus 1, and if I want to normalize it, then I can divide it by 1 over 2. So this is the corresponding eigenvector. This is the correspond. This particular eigenvector is corresponding to eigenvalue lambda equal to minus 1. This particular eigenvector is corresponding to the eigenvalue lambda equal to 1. I hope it is clear. Okay, so I hope it is clear. You can do a few more questions on your own also. But now let us concentrate on a few more important results that are going to be uh, more important for your exam. That are going to be more important for your exam. See, uh, I told you again. I'm writing the general procedure so that if you miss something, then you can understand. So our today's discussion is on. Okay, so I skipped the discussion because I thought it would be too boring for you people. So actually, I skipped the discussion on system of equation that I'll do, that I'm promising to do later on. But first, let us understand how to go about eigenvalues and eigenvectors. So first thing you have to solve is, let's say if I have a matrix M, if I have a matrix M, then I have to solve this equation M minus of lambda I modulus equals to 0. This will give me a characteristic equation. This will give me a characteristic equation. Let us say of order n. If it is n cross n, then there I would get a characteristic equation of order n or degree n. Let us say Cn lambda raised to power n plus Cn minus 1 lambda raised to power n minus 1, and C1 lambda plus C naught equals to 0. Okay, so you will get a characteristic equation here, and on solving the characteristic equation, you can find the eigenvalues. On solving the characteristic equation, you can get the eigenvalues, and once you get these eigenvalues, you have to multiply m minus lambda I with a column vector x. Try to find these column vector x. This is something what you call as your eigenvectors. Okay, this is something what you call as your eigenvectors. So, okay, so I'm just taking a 5-minute break. Meanwhile, I'm going to give you a question that you can solve. Okay, so I'm giving you a question. Please try to solve it on your own. I'm just taking a break of 2 to 3 minutes, and I'm just coming back. Just do this question. Question is very simple. Determine the eigenvalues and eigenvectors of the matrix. Okay, and I would recommend that you see a lecture that I gave on coupled oscillators. If you are doing this eigenvalue problem now, try to see a lecture that I gave on coupled oscillators. It is on the playlist. You can go and watch. It would hardly take the first lecture. And then you will be able to understand the beauty of eigenvalues and eigenvectors of the matrix A given by minus 1, 1, 1, 1, minus 1, 1, 2, 1 and 2. Try to do this. I'm coming in a minute. Try to do this. Okay, so I hope everybody might have got an answer to it. Uh, can I know the eigenvalues you people are getting? I think it's easy to see that eigenvalues would be what? I think eigenvalues would be uh, a minus lambda I mod equal to 0, and I think okay, okay. So what would be eigenvalues to the same? So what would be eigenvalues to this equation? Eigenvalue to this equation would be, okay. Just let me solve it for you. It would be there would be three eigenvalues to this. This would be lambda equals to minus 2, lambda is equal to minus 1, and lambda is equal to 3. So there are three eigenvalues to this. There are three eigenvalues to this. Uh, am I audible or not audible? Okay, so corresponding to these three eigenvalues, so this is easy to solve now. I think this is something that you can solve on your own. So I have to do what? I have to just take a minus lambda I mod equal to 0. And what I will get? I will get 1 minus lambda, I'll get 1, I'll get 1, here I'll get 1, minus 1 minus lambda, then 1, and then I'll get 2, I'll get 1, and I'll get 2 minus lambda, and this mod equal to 0. Okay, so this is one thing that you should understand. And now I should solve this particular thing. I think I can solve this particular thing as, so I'll get 1 minus 1 minus lambda, which is I think minus of 1 plus lambda, and then you have, okay, so people are not attending this. Okay, I think if you, okay, so what you'll get from here, and then inside what do I have? I have minus 1 minus lambda into 2 minus of lambda minus of 1. Okay, then I will have minus of 1, then I can write what I can write, uh, this would be 2 minus lambda and minus of 2, and then plus 1, and then I have this 1 plus 2 times lambda plus 1, I think. Okay. Okay, so I think this is absolutely clear. This equals to 0. Now let us solve this particular equation, and what I'll get, I will simply get, I think this is 1 minus minus plus, so this will become 1 plus lambda whole square, then 2 minus lambda, this minus I take inside, so this will be, I think, simply 2 gets cancelled with 2, so 2 gets cancelled with 2, and then you will have this only lambda here, so I'll have a lambda plus 1, and then I have, I think, this is lambda plus 1, and this is, I think, 2 lambda plus 2 equal to 0. So this is 1, and this is this. From here I'll get simply, this 2 gets cancelled to 2. So I have this minus lambda minus 1, this is plus lambda. And I think from here it's easy for you to solve. I think it's easy for you to solve from here. So let me solve it for you. So lambda square plus 2 lambda plus 1 times 2 minus of lambda, and then you have this plus lambda plus 1, and then you have this 2 lambda plus 2 equal to 0. Solve it. I think this is quite easy to see that if I solve it, I'll get what? So I'm going to take first terms which are in lambda square. So this is 2 lambda square, and then I will have a lambda cube. So I will have a lambda cube. This is the highest power that I can have, minus lambda cube. I will get 2 lambda square from here, and then I will again get a 2 lambda square. So forget about it. So there would be no term in lambda square. How many terms in do you think in linear power there would be? So there would be one term from here, minus lambda, 2 lambda, 3 lambda from here, and then 2 lambda from here, and one more lambda from here. I think this would be 4 and 3. There is a mistake. What? 1. Okay, so this is, I think, 1 plus 2 lambda plus 2. Okay, 1 plus 2 lambda plus 2. So this would be 3. Okay, so what I have written minus 1. This is minus 2 plus 1. So I think I should get minus lambda square. Then 2, 2, 4, 4, and 2 is 2. Minus lambda is minus lambda. 4 from here, 4 from here, 3 from here, 3, 4. There is, I think, some mistake. I think somewhere. Where has the mistake happened? Please let me know what would be the complete answer to this. I mean, the equation to this, what you are getting. So this is quite difficult for you to say in detail. Okay, so let me solve it for you. I think lambda square plus 2 lambda plus 1, 2 minus lambda plus 1 plus lambda. Okay, 1 plus lambda I have forgotten something. Okay, this 1 plus lambda I have forgotten. So I have to write an additional 1 plus lambda also. So I have to write an additional 1 plus lambda also. Okay, so this lambda we forgotten, right? So this lambda we forgotten. So this lambda I'm writing it here. Okay, so now I think the equation should be uh, minus lambda cube. There is no term in quadratic, that is fine. The linear term would be 2, 2, 4, and then minus 3, I think it is plus 3 lambda, then 4 lambda, 6 lambda, 7 lambda, sorry. So this would be 7 lambda, okay? This would be 7 lambda, and what would be the constants? 2, 2, 4, 4 and 2. Uh, how many constants are there? So this is 2 here, 3 is here, 5 is here, and 6 is here. Okay, so there are the total constant is 6. I think this is quite easy to solve. I think you just place lambda is equal to 1 here, so you'll get minus 1 plus 7, which is plus of 6. No, it's not going to work. Place lambda is equal to minus 1. Place lambda is equal to minus 1. Place lambda is equal to minus 1. This would be 1. This would be minus 7 and plus 6. So clear. So lambda minus 1, if I place, it implies I have to divide by lambda plus 1. So I'm dividing it by lambda plus 1. So this will be minus lambda square. This gets cancelled, and minus lambda square will come plus. So I have to do minus of, sorry. Uh, now next what I have to do? See, I have to take. I have taken minus lambda square. This will give you minus lambda square. In order to negotiate with minus lambda square, I have to take again minus lambda. So it will give me minus lambda square plus cancelled, and then this will be. I think this is minus lambda. So I'll get a minus lambda plus. But that is not going to help me. What is an issue? So let me solve it for you at ढंग से कर लेते इसको. I thought you might have got an answer till now, so therefore I was waiting for it. Okay, let me solve it for you. Okay, so what I'll do, I'll use this lambda is equal to minus 1, so I'll divide this entire polynomial by lambda plus 1. So if I divide it by entire this equation by lambda plus 1, I'll get minus lambda cube plus 7 lambda plus 6. Okay, now solve it. It will be minus lambda square. This will be minus lambda cube plus a sign. Cancel it. Okay, so cancel it. Now this will give you again a minus lambda square. And if I am having a minus lambda square, I have to take a minus of lambda. I will get minus of lambda square here. Okay, I'll get a minus of lambda square here. And if I make a plus, then it gets cancelled. Okay. And if I have to solve it, this will be lambda. So if I do this minus lambda, then I'll get 6 of lambda, I think plus 6. So I think this would be simply plus 6. So what am I getting? I'm getting lambda plus 1 into minus of lambda square minus of lambda and plus 6. Okay, this is what I'm getting. So I think this is quite easy to solve. So it will give me lambda is equal to minus 1, and then I'm going to get something like lambda square plus 3 lambda minus 2 lambda and minus of 6 equal to 0. That implies I'm getting lambda is equal to 2. Lambda is equal to, I think this is minus 3 and plus 2 I should write. So I'll get lambda is equal to minus of 2 and lambda is equal to 3. So I'm getting 3 eigenvalues here. So the total eigenvalues will be 3. There will be 3 distinct eigenvalues to this equation. There would be three distinct eigenvalues to this equation. There would be 3 distinct eigenvalues to this equation. I hope it is clear. And these 3 are lambda is equal to minus of 1, lambda is equal to minus of 2, lambda is equals to 3. I hope it is clear. Okay, and if I want to find the eigenvector, uh, okay, so let me find it for one of them. Let us say I'm finding it for lambda is equal to -2, and rest of them I'm leaving to you as a homework. So just try to find these two corresponding to these two eigenvalues, find an eigenvector as a homework. Right now I'm finding it for lambda is equal to -2. So if I'm using lambda is equal to -2, what I will get? What was the original matrix? If I remember, the original matrix was this. Okay, this one minus one, 2, minus 1 minus 2. Okay, so if I remember, this would be the original matrix. I'm just finding the eigenvector corresponding to -2. The remaining one you have to find it at your own pace at home. Such questions are not asked in the examination, but again, I'm saying since you have had enough of break from all these kind of studies, and probably not everyone is equally paced, so I actually do all these questions uh, one by one. Otherwise, you'll not be able to gain anything out of this course. So what I'll do, I'm finding it for this. So a minus lambda I, and then you have this x equal to 0. I have to write this way. So what I'll get, I'll multiply with the column vector, I'll multiply it with the column vector, and that I'll get, it gives me 1 here, it gives me 1 in the second row also, and it gives me, I think, 2 minus 2 is 4. So 2 minus 2 minus 2. So I'll get this 1, I'll get 1 here, and I'll get 4 here. I think it is quite easy to see. This would be 1, this would be 1, this would be 1, this would be 1. Here you'll get 2, here you'll get 1. And this entire thing times an eigenvector of the same order. So I'm writing eigenvector 3 cross. So this is like x1, x2, x3. Now you have to find this x1, x2, x3. I have to find x1, x2, x3. So I will have three equations here. Three distinct equations, three different equations are coming. I'm getting x1 plus x2 plus x3 equal to 0. Then I'm getting another equation as 2x1 plus x2 plus 4x3 equal to 0. This is another equation, and one of the equation is, I think, overlapping, so that will not give you anything. So from here, what I can do, I can subtract. One thing is I can subtract. If I subtract them, I'll get rid of x1 at least. So if I subtract, I will get minus of x1 minus of 3x3 equal to 0, or in other words, I can say x1 is equal to minus of 3x3. This is 1. And what I can do, if I can multiply by 2 and then cut it down. So this will be x2 minus of 2x3. So I'll get x2 is equal to 2x3 here. So this is two, these are two things that we can do. What I can do, I can choose x3 as something. Let's say for simplicity, I'll choose x3 equals to 1. So what I'll get, the eigenvectors to this particular problem, I'll get as -3, I will get as 2, I'll get as 1. And if I want to normalize it, then I can also normalize it using 3 square is 9, 2 square is 4, 13, and 1 upon root 14. So I can divide it by 1 over root 14 to normalize it. If you don't want to normalize it, fine. It's not necessary. I hope this is something that you're getting. Okay. One thing I'm asking, are you not getting bored now? I think if it's that the case, please let me know. I mean, I can also skip all these things for your convenience, but just want to know that is that pace right, or should I increase the pace? Will that be fine, or should I go in this pace only? Obviously, not the entire course I'm going to go through this pace, but only, just let me know in the comment section. Should I go ahead and go fast, or is that fine? Well, is the pace fine? I'm so sorry. Okay, so good enough. Okay, uh, why I'm telling this is, see, if at all I will go very fast, then also there are few things that you may not be able to know. And probably, let's say in interview, somebody asks you what is the rank of a matrix, then you may not actually argue with him that it was not asked in the examination. Because see, in interview panel, there may be a person in mathematics also. There may be a person in mathematics also. And let's say he's sitting in a physics interview, and now he's taking your interview, and you are well versed with eigenvalues, but you are not knowing rank of the matrix, then it does not look good now. So you should, at least you should have some idea about all these things. So that is why I've given an idea. I have skipped a topic because I thought people are not taking interest. So actually I jumped over to eigenvalues and eigenvector directly. Okay, now let us do a few questions. Let us do a few properties, and then we'll do a few questions on eigenvalues and eigenvectors, and then we'll take this further from here tomorrow. And this is an important topic. Please understand. Please keep enough focus at this particular point, because this is what is usually asked in the examination. Now, first point that one needs to remember, that if a matrix is diagonal, so if a matrix is a diagonal matrix, if a matrix is diagonal matrix, then diagonal elements will give you eigenvalues. Then diagonal elements are nothing but they are the eigenvalues itself. They are eigenvalues themselves. For example, if matrix is diagonal, what will happen? All the off diagonal elements are zero. So all the off diagonal elements are zero, and you will have all these elements here: m11, m12, m13, and dash 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 mnn. Let's say this is your matrix M. So all the eigenvalues are nothing but they are the diagonal elements of this matrix. So these are the eigenvalues. These are your eigenvalues. Okay, now let us understand a few more properties. And why this is so, this is quite easy to see. If I have this matrix and if I make a characteristic equation out of it, then what I'll get? I'll get m11 minus lambda, m12 again I'll get minus, m22 minus lambda, I'll get m33 minus lambda, so on and so forth. mnn minus of lambda, and I have to take a determinant here. So I have to open my determinant through this particular side only, because here it is 0, here it is 0. So what I'll get? I'll simply get m11 minus of lambda, m1 m12 minus of lambda, and dash 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 mnn minus of lambda equal to 0. So your set of eigenvalues is nothing but the diagonal elements. Your set of eigenvalues are nothing but your set of eigenvalues are nothing but they are equivalent to diagonal elements themselves. So this is m11, m12 dash 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 mn. So for diagonal matrix, all the diagonal elements form the set of the eigenvalues. Okay, so this is your eigenvalue spectrum. Okay, second property that we should that we should write here. I'm just writing it here. So now what is happening? If you remember, I told you one thing. So second property, I'm writing it here. Okay, if you remember that when I was solving this m minus lambda I determinant equal to 0, I was getting a characteristic equation, isn't it? I was getting a characteristic equation. I was getting a characteristic equation. And let us say this characteristic equation was what? Let me write it as, let's say if I solve this and uh, I'm getting n roots. Let us say lambda 1, lambda 2, lambda 3, dash 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 dash, lambda n. Let us say that when we solve this characteristic equation, we are getting n roots. That is lambda 1, lambda 2, lambda 3, dash dash dash, lambda n. And then if I want to solve, if I have to write the equation, so I told you that this equation is called as the characteristic equation. This equation is called as the characteristic equation, and this characteristic equation is an equation of n degree. This equation is an equation of n degree. So nth degree characteristic equation we are getting, right? Now, if someone asks you in the examination that if I want to write a characteristic equation, can I relate the coefficients of characteristic equation? Can I relate coefficients of characteristic equations with the eigenvalues? Yes, indeed you can. A few of them, a couple of them I'm showing, and then the rest of them I'm not going to write, because this is something from theory of equation you should know. Okay, so probably you will not be that aware, but I'm just showing you. So let us say that the characteristic equation that comes out by solving the secular determinant is Cn lambda ki power n, Cn minus 1 lambda ki power n minus 1, Cn minus 2 lambda raised to power n minus 2 dash dash C1 lambda plus C naught equal to 0. Let us say that this is your characteristic equation. If you remember, when your equation was ax square plus bx plus c, just remember, if you remember, this c was what? This was product of roots, if you remember. Okay, so you can represent your c by a as product of root. You can represent your minus b by a as sum of roots, if you remember, for a quadratic equation. Similarly, for n-dimensional equation, we can do a few things. The first thing is the last constant is C naught. This C naught can be related as product of eigenvalues. I can relate this as product of eigenvalues. And just next to this C n, it is equals to minus 1 raised to power of n minus 1, and then I can write lambda 1 plus lambda 2 dash 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 lambda. Okay, so I can write this way. So lambda 1 plus lambda 2 dash 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 lambda n. Okay, so I hope it is clear. Okay, why this is there? If you see, if I'm doing a quadratic equation, let's say I'm doing a quadratic equation, then what used to happen? Let's say I'm writing a x cube plus b x square plus c x plus d equal to 0. Then this d will give you the product of root. Then this will give you minus this. You can write it as d upon a as product of root, minus of sorry c upon minus of c upon a as something alpha beta plus beta gamma plus gamma delta, and b upon it. So here it is b upon it. It is not minus b upon a. Here it is minus b upon a. So you have to use this minus 1 raised to power n minus 1. You have to use minus 1 raised to power n minus 1. Okay. Okay. So one thing is clear. One thing is very much clear, that this is how you can relate a product of roots and the sum of the roots by the coefficient of this thing. Now you just think of one more thing that I'm telling you. See, till now everything is clear, I guess. Now you see, if I want to write if I want to write the secular determinant, what would be the secular determinant? If I'm taking the matrix M, the secular determinant will be m11 minus lambda, m12, and then I'm having m1n here written, and then I can write m21, m22 minus lambda dash 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 m2n, and then this is mn1, this is mn2, and dash 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 mnn minus lambda. Okay, now I have to solve this characteristic equation, and if this determinant when solved gives you a characteristic equation, so this gives you a characteristic equation which is written here. So this gives you a characteristic equation. So this gives you a characteristic equation. Let's say Cn lambda n plus Cn minus 1 lambda n minus 1 dash 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 C1 lambda plus C naught equal to 0, isn't it? Okay, so basically what is happening? This particular thing is equivalent to writing this. This particular thing is equivalent to writing this. Now just consider one of my statement. If I take lambda is equal to 0. If I take lambda is equal to 0, what am I going to get? I'm going to get that my C naught is equals to what? It is equals to determinant of M. So this minus lambda will vanish, and this C naught will come as determinant of M. And I've just now solved that the C naught is equal to product of eigenvalues. So always remember, the product of eigenvalues is equivalent to, so your product of eigenvalues is equals to the determinant of the matrix. Is that clear? This is a standard result. Please do remember it. I have just briefly sketched an idea as to how you can relate. But overall, you should remember that the product of eigenvalues is equals to equal to determinant of m. Is that clear? Okay. So is that clear or not? I hope it is clear. Okay. Now, if I want to relate it to sum of eigenvalues. If I want to relate to sum of eigenvalues. Now just remember uh, a little bit ago, a little bit ago, so I'm writing sum of eigenvalues. So what was sum of eigenvalue according to the characteristic equation? If I'm writing lambda 1 plus lambda 2 plus lambda 3 dash 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 lambda n, this is equal to nothing but it is equals to the trace of matrix. Okay, sorry for the interruption because of the network issue. Now, I'm just writing a few more, you can say, results that are very important for you. Okay, that are very important for you. Those results will really help you out in doing all these problems. Okay, so till now we have done that the product of eigenvalues is equals to the determinant of the matrix and the sum of the eigenvalues is equals to the trace of the matrix. This is something that we have already done till now. Okay, now we are moving a little bit further, and let us see what all more results we can write. So two of those important results have written. Why I'm not deriving this? Because see, I will have to solve this particular equation here. So if you are willing to solve it, then it is fine. Otherwise, even if you are not willing to solve, it's absolutely fine. What you have to do, just if you want to really do this also, just I'm just writing. I'm giving you a hint. Try to expand. Try to expand the determinant m minus lambda I. Okay. Try to expand this equal to 0. Compare the coefficient. Compare the coefficients. Compare the coefficient of lambda raised to power n minus 1. Compare the coefficients of lambda raised to power n minus 1 on both sides. And I know here the lambda raised to power n minus coefficient is simply Cn minus 1. And I taught you that Cn minus 1 can be related to the sum of the eigenvalues. And we know that Cn minus 1 can be related to the sum of eigenvalues. And eventually what you'll get that sum of eigenvalues is nothing but it is equal to the trace of the matrix. This is an idea I'm giving you for your proof part. Okay, just an idea. All you need to do is just expand this. Try to compare lambda raised to power n minus 1. Try to compare lambda raised to power n minus 1. We know that Cn minus 1 is nothing but it is equal to the trace of the, it is equal to the sum of the eigenvalues. Okay, so this is one thing that you should remember. Now one important result is that if the matrix M, if the matrix M is non-singular, if the matrix M is non-singular, that is, if we have a non-singular matrix M, if you have a non-singular matrix M with eigenvalues lambda 1, lambda 2, lambda n, then the eigenvalues of the inverse, then the eigenvalues of inverse M are 1 upon lambda 1, 1 upon lambda 2, dash dash dash, 1 upon lambda respectively. Okay. In this, we just use one fact, that is determinant of A into determinant of B is equals to determinant AB. So this is a result that you can use, and then it is quite easy to see that let us say instead of A I'm writing M, and instead of B I'm writing M inverse. The determinant of identity is simply so so what I can do, so I can, instead of this thing, I can do one more thing. Another way I can do this thing. I know that for eigenvalue, so for eigenvalue, I'm just writing it here somewhere. So just giving you a hint. Okay, just giving you a hint. So I know that I'm solving determinant of m minus lambda I is equal to 0. This is what we want to solve. If I have to find the characteristic equation, this particular determinant is solved. If this determinant is multiplied by, I'm writing this determinant is multiplied by m inverse upon lambda. Multiply this determinant by m inverse upon lambda, you will get determinant m minus of lambda I, m minus of lambda I into determinant, determinant m inverse upon lambda into determinant m minus lambda I is equal to 0. And from here you will get determinant, this will be determinant A into determinant B, this will be determinant AB. So this will give you m inverse m upon lambda minus of m inverse upon lambda into lambda I. And here you will get determinant of 1 upon lambda minus of m inverse equal to 0. Or in other words, I can say determinant m inverse minus lambda minus 1 times identity is equal to 0. So when we were trying to find the eigenvalues for m, it was equivalent to solving this characteristic equation. And this characteristic equation, when we are getting, it implies from here, I can say that the lambda minus 1 are corresponding eigenvalues for m inverse. Lambda minus 1 are the corresponding eigenvalue for m inverse. This is something that you should understand. Another important thing with regards to eigenvectors you should remember. Before that, let me just write a small result also. Another small result that you should that you should remember. Let's say if a matrix has real elements only, if the matrix has real elements only, then eigenvalues may or may not be real. That is, we can say that eigenvalues are not necessarily real. It is not always necessary that if all the elements are real, then eigenvalues are also real. So just remember, just keep it as a note. Note that if matrix has real elements only, then eigenvalues are not necessarily real. Okay, just for an example, I'm giving you one example. Okay, just giving you an example. Let us say I take 0, 0, and I take 1 here and minus 1 here. So what it will yield me? It will yield me lambda square is equal to minus of 1. So from here I'll get lambda is equals to plus minus of iota. However, you can see that this particular matrix contained all the real values. It contained all the real values, all the elements are real, but eigenvalues are imaginary. Eigenvalues are imaginary. Okay. Now there are a few things corresponding to eigenvectors that I will do a little bit later. But let us first solve a few questions that have come in the examination, so that you will be able to understand the applicability of all these properties that I have listed. Okay, so applicability of all these properties as I have listed just before. So then it will be easy for us to understand that why I have shown you all these kind of properties. Let us say one of the question that came in the exam, and where we can directly apply this thing, that I'm going to do it first for you. So let us say there's a question in net exam only. Okay, so it is from net exam only. So in net exam, nobody is going to ask you big questions. Everybody is going to ask you simple questions only. Okay, simple as in, matlab, you want to solve this particular, you want to have this particular. If you have these two things in mind, that is trace of matrix is equal to the sum of eigenvalues, and product of matrices is equal to the product of matrices. Product of eigenvalues is equal to the determinant of the matrix. If you know both of these results, then you can write answer to most of your problems. Let 3 cross 3 matrix, let 3 cross 3 matrix M be such that trace of M, is equals to 6, trace of M square is equals to 26, trace of M cube is equal to 90. Trace of M cube is equal to 90. Which of the following, whenever I write WOTF, then it implies which of the following can be a possible set of eigenvalues. Okay, but before I do it, I'll give you one more property, uh, which can be a possible set of eigenvalues of M. So I'm giving you first option as 1 comma 1 comma 4. Then second option is minus 1 comma 0 comma 7. Then third option is minus 1 comma 3 comma 4. And the fourth option is 2 comma 2 comma 2. Okay, so these are the options. A 3 cross 3 matrix is given to you, and then it is given to you that the trace of matrix M is simply equals to trace of matrix M is equal to 6, trace of matrix M square is equals to 26, and trace of matrix M cube is given to be equals to 90. Then it is asked what can be the possible values of, what can be possible eigenvalues of M. What can be the possible eigenvalues of M? This is what has been asked. Just think about it and let me know. I'm giving you 2 minutes to solve this particular problem. Okay, if you don't remember the result, I'll give you the result also. I'll give you the result also. See, always remember, as we did in the as we did for the non-singular matrix, we wrote one result. Now we wrote one result that if lambda are the corresponding eigenvalues to M, then lambda inverse will be the corresponding eigenvalue for M inverse. Similarly, if if you can say I'm writing M has a set of eigenvalues given by lambda, then M square, the eigenvalues will be squared. For M cube, eigenvalues will be cube, so on and so forth. So for the matrix M raised to power n, the eigenvalues will be like this. I hope it is clear. I mean, this is just a result that I'm sharing with you, because I'm not deriving this result for you. Just remember this result. What I have told you that if the trace of the matrix, if the eigenvalues are lambda for a matrix M, then the eigenvalues for M square would be lambda square, eigenvalues for M cube will be lambda cube, so on and so forth. You have to remember this result. Okay, so this is quite easy to see now. So for example, if I do this mx, just I'm writing it so that you should get my point what I want to say. See, mx is equal to what? It is equal to lambda x. Now pre-multiply with m. So you'll get m square x is equal to what? Lambda mx. And what it is equal to? It is equal to lambda square x. So corresponding to m square, the eigenvalue would be lambda square. Corresponding to m cube, the eigenvalues would be lambda cube. Okay, so this is quite easy to see. Just let me know the option. Which of the following do you think is right? Which can be the possible set of eigenvalues? Just use the option. In exam, it is not always necessary that you come out with a proper solution. In exam, since the exam itself is giving you options now, so you just use the options and do the question. You just use the option and do the question. Okay, just use the option and do the question. That will be a fruitful approach here. So if I use this approach, uh, if I use this approach, what will I get? So if I use this approach, let's say I'm writing the trace of m raised to power n would simply be equals to what? Summation lambda I raised to power n, where lambda I are the eigenvalues of m. Lambda I are eigenvalues of m. Now I already know that lambda square, this trace of m square would be lambda 1 square plus lambda 2 square plus lambda 3 square. Similarly, trace of m cube would be lambda 1 whole cube plus lambda 2 whole cube plus lambda 3 whole cube. Okay, and what would be trace of m? Trace of m would be lambda 1 plus lambda 2 plus lambda 3. Now, if you see, if I just take options and try to use it, then just reverse, just try to write, try to find what would be the best answer to this. So, for example, okay, so 7 cannot be the case because 7 cube is 343. Forget about it. So it is too large. I know that 7 cube will be 343. And in any case, this minus 1 is not going to. So I have this thing, trace m cube should be 90. So I think this should be an answer. See, because 4 cube plus 3 cube minus 1. Okay, so what is 3 cube? 3 cube is 27, 4 cube is 64, minus of 1. So it will give me 64 plus 26, which is 90. Fine. And if I square it up, so 1 square is 1, 2, 3 square is 9, 4 square is 16. So 16 plus 1, 17, plus 9, 26. This is fine. And trace of m is should be 6. So 6 is given by this also, 6 is given by this also, 6 is given by this also, and 6 is given by this also. So answer should be C. I hope it is clear. Okay, so I think these are very easy questions for you. Now I'll give you a little bit difficult question, and now let us see how many of you can answer this question. Okay, now comes a elephant. Okay, so, okay, so now just let me know this particular question, that let's say I have this, just give me a minute. Okay, okay, just give me a minute. I think. Oh, just give me a minute. I'm going to reinitialize this. Just give me a minute. Okay, so let us do this problem that I'm giving it to you. Just think about it. Okay, just think about it. A little bit difficult. Not little bit. This is quite difficult. But let me see how many of you can make an understanding out of it. How many of you can make an understanding out of it? Okay, just give me a minute so that. Okay, just give me a minute. Okay, just think about this. Okay, just give me a minute. Just giving me a hard time. Just bear me for a minute. Okay. Okay. Next I'm giving you another question again from net exam only first, and then I'll give you a bigger question because that is slightly difficult for you. So let me give you some easy questions at first, and then I'll ask you some difficult questions also. So now I'm asking you a simple question from net attempt only. So okay, so this was also asked in net exam only. So I'm writing which of the following cannot be the eigenvalues for a 3 cross 3 matrix? Which of the following cannot be cannot be the eigenvalues cannot be the eigenvalues for a 3 cross 3 matrix for a 3 cross 3 matrix? Option number 1, which was given in the exam, was 2 iota, 0 minus 2 iota. Option number B was 1 comma 1 comma 1, cannot be, remember. Option number C was e की power iota theta, e की power minus iota theta and 1. And option number D was iota 1 and 0. What do you think would be an answer to this? Okay, so this question is not that much of eigenvalues and eigenvectors, rather it is of basic understanding. Okay, basic understanding of what? Basic understanding of calculus. See, always remember, I'm writing it here, always always remember. What you have to remember? Always remember that every odd degree polynomial has at least one real root. At least one real root. I mean, this is a kind of extension from intermediate value property of continuous functions, but that is something that you don't know. But just giving you an example, let us say I'm writing a polynomial with the leading term x raised to power n, where n is odd, where n is odd. Okay, all the terms are there. I'm not bothered about it. Just think that I'm talking of a polynomial with the leading term x raised to power n, with leading term a naught x to power n, where n is odd, and let a naught be positive. Now just think about it. As x tends to infinity, where your px would go? Your px would go towards infinity, isn't it? And as x tends to minus infinity, where your px would go? It will go towards minus infinity. So if your function, while traveling from minus infinity to plus infinity, is going from minus infinity to plus infinity, at least one real root is guaranteed. At least one real root is guaranteed. Why I'm stressing upon this is a student of mine was selected at interview for Aizen Mohali, and he was asked a question of image problem, and he got stuck with the cubic equation, and he was not able to find an answer to this. What he should have done in the interview, he should have told to the interviewers that, see sir, this is an odd degree polynomial, it will always have a it will always have at least one real root. So real root is guaranteed, there would come a solution. I'm not able to justify what is the solution right now because I'm not well versed with the solving polynomials, but At least that calculus knowledge would have helped him. But however, he could not have, he did not solve it. Now you see, just think about this. I'm saying it's not that it will always have one real root. It may be so possible that it goes here and then and here and there and here and there and here and there and then goes out. That this way also it can happen. But at least one real root is guaranteed. At least it will always have one real root. Now think this thing. Now think about this particular concept in the scenario of cubic equation, because after all, if you have a 3 cross 3 matrix, the characteristic equation to this 3 cross 3 matrix would be a cubic equation, right? Now think about this. What are the possibilities for a cubic equation to have roots? There can be 3 real roots. Indeed, just writing the possibility. There can be 2 real roots and 1 complex. Just writing the scenarios, okay? There can be 2 complex roots and 1 real, and there can be 3 complex roots. Now, from theory of equation, we know that always complex roots are are followed by their conjugate counterparts. Are followed by their conjugate counterparts. What do I mean by when I say this? I mean to say that if a plus iota b is a root, then a minus iota b will always be there. So always remember, the number of complex roots can always be even only. Because if a plus iota b is there, so a minus iota b would follow. So number of complex root will always be even. Will always be even. So 3 complex root cannot be the case. Forget about it. 1 complex root cannot be the case. So for a cubic root, either there can be 3 real roots or there can be 1 real root or 2 complex root. So from here also you can see that 1 real root is guaranteed. What I want to say is that in a cubic equation, either there can be 1 real root and 2 complex roots, or there can be 3 real roots. So in general, I can say now at least 1 real root is guaranteed. At least 1 real root is guaranteed. Now think about all these things in this scenario, in the question sense. So yes, for a 3 cross 3 matrix, yes, if 2 iota is one of the roots, minus 2 iota will be one of the roots, and 0 can be another real root. So there can be 2 complex roots. One is conjugate of another. Another root can be real one. So this cannot be an answer. See, please remember, question was asked which cannot be a real root, which cannot be eigenvalue, which cannot be eigenvalue. 3 real roots can be there. So this is also not possible. We are asked which cannot be eigenvalues for 3 cross 3. If e ki power iota is there, e ki power minus iota would be there, 1. So there can be 2 complex root, 1 real root. Okay, this cannot be an answer. But just think about this. Can there be a complex single root? No, not at all. So this is the correct answer. The option number D is the correct answer. Is that clear? Or is that not clear? Please let me know in the comment section. Is that clear? Okay, good enough. So I hope this is enough for today. I know I'll give you a question which is slightly tricky, and probably you may not be able to get the answer for that. Uh, okay, so let us do a few more easy questions and then we'll move to a difficult question. Okay, let us do a few more easy questions and then we'll move to difficult question. Okay, so just think about this. This particular question was asked in JAM exam, and the question says that the trace of a 2 cross 2 matrix, is given to be equal to 4, and the determinant is given to be equals to 8. If one of the eigenvalue is, if one of the eigenvalue is, if one of the eigenvalue is 2 times 1 plus iota, what would be other eigenvalue? What would be another eigenvalue? So if one of the eigenvalues is given to be equals to 2 1 plus iota, what would be the another eigenvalue? Okay, this question, if you have listened to me very carefully in the previous one, you don't even need to see this. Just write answer to 1 minus iota. Clear. It's all over. Why? I told you that whenever there is a complex root, and since it is a 2 cross 2 matrix, just think about it, that the characteristic equation would be what? The characteristic equation would be simply a quadratic equation. And if one of the root is 2 times 1 plus iota, the other root will be obviously conjugate. There is no, don't even think about these two things. They are given to you, but you could have directly marked an answer. Now you can verify on your own self also, that if this is your lambda 1 and let's say this is your lambda 2, what would be lambda 1 plus lambda 2? The trace of matrix is given by the sum of the eigenvalues. Clearly it is equals to 4. What is lambda 1 into lambda 2? Clearly you can see this would be 2, 1 minus iota, 1 plus iota, 1 minus iota square, 1, so it would be, I think, 8. It is quite easy to see. But just think about, just think what I taught you just a few minutes before. That I told you that if one of the eigenvalue is complex, the conjugate of it will always follow. Conjugate of it will always follow. So if you have a 2 cross 2 matrix, then the characteristic equation will be a quadratic equation. And if it is a quadratic equation, then obviously one of the root is 2 into 1 plus iota, the other one would be the conjugate of it. There is not even a point to see the correctness of these two things. You can just verify. You can just verify this would be the root. This would be the other eigenvalue. Is that clear? Okay, now consider one more thing that I'm giving it to you. Uh, I think this is a difficult question. This is extremely difficult for you, but I'm just giving it to you. And I'm telling that this was once created by me in the class, and the same question was asked in Chennai Mathematical Institute paper, I think, or interview. So, however, I'm easing things for you. I'm not using terms like positive definite matrix. I'm just giving you, consider an n cross n matrix. Consider an n cross n matrix A, which have which has distinct positive eigenvalues only, which has distinct positive eigenvalues, lambda 1, lambda 2, lambda 3 dash 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 lambda. Let us consider A, the n cross n matrix having distinct positive eigenvalues lambda 1, lambda 2, lambda 3, lambda n. So I am writing that lambda I would be 0, where lambda I is 1, 2, 3, 4 dash 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 n. Okay. What would be the what would be the uh, minimum value of trace A raised to power n? Trace A raised to power n. What will be the minimum value of trace A raised to power n? Don't worry, you will not be able to do it. Let me do it for you. Okay. So if I'm considering a matrix A which is of n cross n, if I'm considering a matrix A which is of matrix A n cross n, then you see the trace of this matrix can be written as the sum of the eigenvalues, isn't it? So I can write lambda 1 plus lambda 2 dash 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 lambda n. Okay, now just think about two things that I'm referring here, and this is an important inequality in mathematics. Okay, just think about this thing, x1 and x2. If there are two positive number, it is always greater than equal to root over x1 into x2. Okay, this is called as your arithmetic mean, and this is called as the geometric mean of two positive numbers. X1, x2 are positive numbers. This inequality, when generalized for n terms, can be written in this fashion: x1, x2, x3, xn divided by n is always greater than equals to x1, x2 dash 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 xn raised power 1 over n. So arithmetic mean of n positive numbers is always greater than equal to geometric mean of n positive numbers. Okay. So now I have to find trace a raised to power n. So what is trace a? Trace a is lambda 1, lambda 2, dash 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 lambda n. And what would be the determinant of a? The determinant of a would be lambda 1 into lambda 2 dash 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 lambda n. All of them are positive. Now let us apply this arithmetic mean greater than equal to geometric mean. So lambda 1 plus lambda 2 plus lambda 3 dash 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 plus lambda n divided by n is always greater than equal to lambda 1 into lambda 2 into lambda 3 dash 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 lambda n raised power 1 over n. So what am I getting from here? I'm getting that trace a is always greater than equal to determinant trace a divided by n is always greater than determinant a raised to power 1 over n. And from here, if I take n both sides, so I can write trace a raised power n is always greater than equal to n raised to power n times determinant of a. So what do you think the minimum of trace a raised to power n would be? So the minimum of trace a raised to power n would be simply n raised to power n into determinant of a. I hope it is clear to you. I hope it is clear to you. Please let me know if there's a problem with this question. Please let me know if there is a problem with this question. But if there's no problem, then I can move a little bit more. Okay. So this particular problem was lately asked in Chennai Mathematical Institute, I think, for interview or something. Okay. So actually, when I teach mathematics students, so basically, then I find that um, the inequalities play an important role. Okay. So when inequalities play an important role, then we should understand that we should know them to great detail. Okay. So just giving you a minute, just giving you a little bit, just okay. Okay, just give me a minute and then I'll take another problem for you. Okay. Okay, just think about this. Just think about this and give me an answer to this problem. Okay, just think about this. So question is that let A be a 3 cross 3 matrix. Let A be a 3 cross 3 matrix with real entries. With real entries. So A is a 3 cross 3 matrix with real entries. Okay. Now the determinant of A is given to be equivalent to 6. The determinant is of A is given to be equivalent to 6, and trace A is given to be equal to 0. Trace A is given to be equivalent to 0. If determinant of A plus I, that is determinant of A plus I identity is equal to 0, if determinant of A plus I is equal to 0, where I denotes a 3 cross 3 identity matrix, then the eigenvalues of A are option number 1 minus 1, 2 and 3, option number 2 minus 1, 2 and minus 3, option number C is 1, 2 and minus 3, and option number D is simply minus 1, minus 2 and 3. Okay, so this was asked in, I think, net exam. Okay, so try to do this question. This is easy question. Don't think that it was asked in net math, so it is going to be very difficult. And that is why I derived the entire thing for you. That is why I derived the entire thing for you. Just think about this. Just think about this, and you will be able to get it. Don't worry. If you're not getting, then obviously I'm there. But just think about this question. Give yourself a minute or so, and if you're then also not you're not able to do, then I'll do it for you. Okay, so just let me know. Okay, see, uh, just understand that it was, if I have this determinant of m minus lambda I equal to 0, what does it imply? It is an eigenvalue equation which is being solved, and this is eigenvalue equation when it is actually solved, we get the secular determinant, and here this lambda is what? This lambda is the eigenvalue, isn't it? Lambda is the eigenvalue. What it is given? It is given that determinant of a plus I is equals to 0. What does it imply? It implies that one of the eigenvalues certainly is minus 1. So one of the eigenvalue you can be sure of is minus 1, right? Yes or no? I hope students are getting it. So one of the eigenvalue would be minus 1, certainly. Okay. Now one of the eigenvalues, if it is equals to minus of 1, then what about the other eigenvalues? Now it's very simple for you to see that if one of the eigenvalues is minus 1, then the other eigenvalues, let us say it is equals to lambda 2 and lambda 3. So now it is easy for you. Minus 1 plus lambda 2 plus lambda 3 should be equals to what? Should be equals to 0. So it implies that lambda 2 plus lambda 3 should be equal to 1. Why? Because trace of eigenvalue should be 0. And product of eigenvalues should be 6. So it implies lambda 2 into lambda 3 must be equal to minus of 6, right? Lambda 2 into lambda 3 should be equals to minus of 6. Now think backwards and use the options. Use the options, because see, in exam it is not said that you have to solve each and every question. If you want to solve an equation out of it, you can do. You can write lambda 2 is equal to minus 6 upon lambda 3, replace it here, a quadratic equation will come, and you can solve it also. So from here, what you can do, you can either write lambda 2 is equal to minus 6 upon lambda 3 and place it in this and then solve a quadratic equation, or use options. So in exam it is like, exam is all about your wittiness, na? So you can be witty there. So just think about which of the option do you think will give you a correct answer. Which option do you think will give you a correct answer? Just think about it. So clearly D option. Okay, so clearly D option. See, minus 2 and 3 multiplied will give you minus 6, and lambda 2 plus lambda 3 will give you 1. Here you have lambda 2 plus lambda 3. It will never give you an answer. Minus 1 cannot be the case. It can never be the case. And lambda 2 plus lambda 3 is 5 here. It cannot be the case. So answer should be what? Minus 1, minus 2 and 3. Is that clear? So always remember, this is an important aspect from where most of the questions are asked. That is trace of the matrix and determinant of the matrix. Most often you are going to see that such questions are going to be asked in your examination. Most often you're going to see that such questions are going to be asked in your examination. So keep in mind these two properties. Well, fix them in your mind. Never forget them. Now, last question for you. Just a last question. Okay, I think it is quite lengthy class. And whoever is attending, please let me know if you've got the answer what I was telling. Is it that you're not getting it? Please let me know. I'm giving you a matrix, just find the trace of it. Trace of a matrix, just find the trace, and then you have this 0, 2, 0, and you have this 0, 0, 3 raised to power 20. Raised to power 20. Find the trace of this matrix. Find the trace of this matrix. Will it be 7 raised to power 20? Will it be 2 raised to power 20 plus 3 raised to power 20? Will it be 2 into, I'm so sorry, 2 into 2 raised to power 20? So sorry, 3 raised to power 20? Or will it be 2 raised to power 20 plus 3 raised to power 20 plus 1? Which of the following do you think that answer would be? What do you think an answer to this particular problem would be? Just think about it and give me an answer to this. It's an easy question, don't worry. It's an easy question. If you're not getting, don't worry, I'll do it for you. What do you think an answer to this would be? I'm just telling you to find trace of 2, 1, 0, 0, 2, 0, 0, 0, 3. Okay. Let's see. Just take a few minutes. If you're not able to solve, then I'll give it to you as a homework. Try to do it as a homework also. So one of the question you can do as a homework also. But I just want to understand that uh, so first let me help you out. Let me help you out. So I told you that if I'm writing it here, if lambda is the eigenvalue for matrix M, if lambda is the eigenvalue for matrix M, that implies mx is equal to lambda x, right? I hope it is clear. Mx equal to x. Then if I do m square x, that is if I pre-multiply m, I'll get lambda square x. So inductively I can say that if I apply m n times, that is if I pre-multiply m times n times, then lambda raised to power n x would come here. So I can say that if corresponding to m, that is matrix m, the eigenvalues are lambda, then corresponding to m and the eigenvalues will be lambda raised to power n. This is clear. So what you are supposed to find? You are supposed to find what? You are supposed to find the, just give me a minute. You are supposed to find the eigenvalues for this. First try to find the eigenvalues for this. Then you will be able to understand what I am telling. First try to find the eigenvalue for this. So what would be the eigenvalues for this? Please let me know. That is something that you can do. I think that is something that you can do. I don't think there is an issue with this. What would be the eigenvalue for this? So just find 2 minus lambda. Here you will have 1, you will have 0. Here you will have 0, you will have 2 minus of lambda, 0. And here you will have 0, 0. And here you will have 3 minus lambda. Okay. Okay, so what you'll get? So you'll get simply 2 minus lambda into 2 minus lambda into 3 minus of lambda, right? So your eigenvalues would be simply, 2, 2 and 3. These are the eigenvalues for m. Let's say this is your m, okay? So let's say this is your m, and we want to find the trace of m raised to power 20. So these are the eigenvalues for m. What do you think the eigenvalues of m raised to power 20 would be? So eigenvalues of m raised to power 20, I'm writing EIG. So if you have used the MATLAB, so there you give this kind of ig m20. What would be ig m20? This would be 2 raised to power 20, comma 2 raised to power 20, and then 3 raised to power 20. Are you getting my point? I told you now, if lambda is eigenvalue for m, then lambda raised to power n will be the eigenvalue for m raised to power n. So now if I want to find the trace of m raised to power 20, what I'll get? I'll get 2 into 2 raised to power 20 plus 3 raised to power 20. Okay? Okay. Now actually I spent some time in calculating the eigenvalues here. But what if I tell you that I would have marked this answer straight C in one go? Not even second I would have thought about it. Not even for a second I would have thought about it. Now you would say, oh no, there would be some trick. No, there is no such trick. Just remember, just remember that, and this is something that I'm leaving for you. I don't think proof is required. If you require a proof, I'll give it tomorrow. But always remember this sort of matrix where these elements, like this is 0, 0, 0, and 0, and other elements are here. Okay, this kind of matrix is called as the lower triangular matrix. And if these zeros are here, then it is called as upper triangular matrix. So this is called as the lower triangular matrix. Always remember the eigenvalues of a triangular matrix are equal to the, I'm writing it here, the eigenvalues of a triangular matrix are always equal to the, diagonal entries are always equal to the so you don't even need to characteristic equation. Okay, are you getting my point? So whenever you have this triangular matrices, always remember the eigenvalue for a triangular matrix is always equal to the diagonal entries. Simple. So you don't even need to find the eigenvalue separately. However, you've seen the same thing happening when I found the eigenvalues, because I was aware that you're not doing this. So that is why I thought, okay, let it be. I hope you've got this particular thing. Please let me know if you've got this particular thing, and then I'll probably do another question for you. Is that clear? Now let us do another question. Last question. Okay, this is the last question. Don't worry. Now see, if A is a 2 cross 2 matrix, if A is a 2 cross 2 matrix over R, that is, it has all real entries over R with determinant A plus I is equals to 1 plus determinant A. It is given that determinant of A plus I is equals to 1 plus determinant of A. Then what can be concluded? Then that what can be concluded? That one can be concluded with certainty. 1. That determinant of A is equal to 0. B. A is equal to 0. C. Trace A is equal to 0. Or D. A is non-singular. A is non-singular. Just think about it. Just think about it. So I'll do it for you. Don't worry. Okay. So what I'll do, A is a 2 cross 2 matrix, and it is over R means the entries are real. So what I'll do, I'll write it here. So just give me a minute. I'll write it here. Okay. So I'll take this matrix A as some A, and some B, and then C and D. Is that fine? So I'm taking A as A B C D. Okay. So I'm taking A as some A B C D. This is, let's say, 2 cross 2 matrix. Done. Now, if this is the case, and what is the condition given to us? The condition given to us that determinant of A plus identity. So A plus identity would be what? A plus 1, B, C, D plus 1, right? So it is equivalent to taking the determinant of A plus 1, B, C, and D plus 1, and it is equivalent to 1 plus determinant of A. What would be determinant of A? It will be simply determinant. I'm using this symbol. Okay, so I should have not used this, because there I have used this now. So 1 plus, it is getting hacked. Okay, so A, B, C, and D. Okay, so this is how it is. Now you just solve this left hand side and right hand side. The left hand side then solved, you will get A plus 1 into D plus 1 minus BC is equals to 1 plus AD minus of BC. 1 plus AD minus of BC, and here you have A plus 1 into D plus 1 minus BC. Now you see AD will come here, A will come here, D will come here, and 1 will come here, and minus BC will also come here, and here you have 1 plus AD minus BC. I hope it is clear. Now see, minus BC gets cancelled with minus BC, AD gets cancelled with AD, and 1 gets cancelled with 1. So what does it imply? It implies A plus D is equal to 0. And by the way, what is A plus D? A plus D is nothing but it is equals to trace of A. So it necessarily implies that trace of A must be equal to 0. So option C must be correct. I hope you are enjoying all these questions. If you have certain doubt in certain areas, do let me know. Overall, this I would strongly suggest that this eigenvalue and eigenvector part, you should prepare it very nicely for your exam, because you see, in most of the exam, whether it is TIFR or JEST or NET or GATE or any of your exam, most of the questions are going to be on the qualitative part of eigenvalues, eigenvectors, or these questions. And that is why I was telling you, keep patience for a few days, and when I'll start doing questions, you'll start enjoying. The only point is, see, as a teacher I have to give you each and everything, because let's say if I'm teaching you and if I'm not teaching you adjoint, and let's say an exam question comes from adjoint, and then you are not able to do, so then it's like, why did I not study it? So that is why actually I'm teaching all these small things. I know where to lay more stress and where to lay less stress. So for example, I can also give you many questions on adjoint which you will not be able to do, but I know the examiner is not going to ask. Being from physics side, they're not going to ask much of the questions from there. From physics side, most of our focus is on eigenvalues and finding eigenvectors. So we'll do many questions here. I hope to meet you tomorrow. Please keep sending your feedback on through comments or through WhatsApp group. Uh, I hope to meet you tomorrow. Till then, take care. Bye bye.